Good morning, everyone. I am Miss Dua Shandio, and I am delighted to welcome you all today. We will be exploring an exciting topic in chemistry. Today's presentation is titled Revised Lecture on Chemical Kinetics. We'll be covering the fundamental concepts of how reactions occur and their rates. I hope you find this session both informative and engaging. Let's get started. Today, we'll be exploring some fundamental topics in chemical kinetics. First up is chemical kinetics itself, which is all about understanding how and at what rate chemical reactions occur. This is crucial because it helps us control reactions in everything from industrial processes to biological systems. Next, we'll look at the rate constant, a key concept that tells us how fast a reaction proceeds under specific conditions. It's like a numerical fingerprint of the reaction's speed, influenced by factors like temperature and concentration. Then, we'll dive into collision theory, which explains how reactions happen based on molecules colliding with enough energy and proper orientation. This theory helps us understand why reaction rates vary and how to influence them. Finally, we'll discuss the factors affecting rate of reaction. These include temperature, concentration, surface area, and catalysts, things that can speed up or slow down reactions. Understanding these factors is essential for optimizing reaction conditions in real-world applications. Throughout this presentation, we'll connect these ideas to get a clear picture of what governs reaction rates and how we can manipulate them to our advantage. Let's take a closer look at the rate of a chemical reaction. Essentially, this tells us how quickly reactants are turning into products, or vice versa. It's measured by observing how the concentration of either reactants or products changes over a specific period of time. The general expression for the rate is pretty straightforward. It's the change in concentration divided by the change in time. So, if we look at a simple reaction, like a turning into B, we can describe the rate in a couple of ways. It could be the negative change in concentration of A over a certain time interval, or the positive change in concentration of B over that same period. It's important to note the negative sign when we're talking about reactants like A that indicates that their concentration decreases as the reaction proceeds. This negative sign helps us keep track of whether substances are being consumed or produced during the reaction. Understanding this concept is fundamental because it connects to the overall theme of reaction kinetics, how fast reactions happen and what factors influence that speed. By quantifying reaction rates, we gain insight into the mechanisms and conditions that affect chemical processes. Let's talk about the rate constant. Denoted as K, this is a proportionality constant in the rate equation, which helps us understand how quickly a reaction proceeds. The general form of the rate law is rate equals K times the concentration of reactant A raised to the power of N here. K is the rate constant, A is the concentration of the reactant, and N is the order of the reaction. What's important to remember is that the value of K depends on temperature and whether a catalyst is involved. However, it doesn't depend on the concentration itself. This means that if you change the concentration, the rate will change, but the rate constant remains the same under constant temperature and catalyst conditions. Understanding the rate constant is crucial because it connects the reaction's speed directly to measurable quantities, allowing us to predict how the reaction behaves under different conditions. It's a key piece in the overall puzzle of reaction kinetics. Let's take a closer look at collision theory. This theory helps us understand how chemical reactions actually happen. Essentially, it states that for a reaction to occur, the reactant particles need to collide with each other. But not every collision results in a reaction, only those that are effective. Now, an effective collision has two key conditions. First, the particles must have the correct orientation. Think of it like a lock and key. Only the right alignment will allow the reaction to proceed. Second, they need sufficient energy, which we call activation energy. This means the particles must collide with enough force to break existing bonds and form new ones. These points are crucial because they connect directly to the overall theme of reaction rates. The more effective collisions happening, the faster the reaction. So, understanding these conditions helps us see why some reactions happen quickly and others take more time. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's talk about activation energy, or E. This is the minimum amount of energy that particles need to have in order for a reaction to actually happen. Think of it as the energy threshold that must be overcome for bonds to break and new ones to form. Now, if particles collide with less energy than E, the reaction simply won't take place. They just bounce off each other without any change. But here's the interesting part. When we increase the temperature, more particles gain enough energy to reach or exceed E. This means that at higher temperatures, reactions tend to happen faster because more particles are capable of reacting. This concept ties into the overall theme of how energy influences reaction rates. Essentially, the more energy particles have, the more likely they are to react, which explains why temperature plays such a crucial role in speeding up chemical processes. Let's take a closer look at some of the key factors that influence the rate of a reaction. First up is the concentration of reactants. When you increase the concentration, you're essentially packing more particles into the same space, which means they're more likely to collide. This increase in collisions typically speeds up the reaction. Next is temperature. As temperature rises, particles move faster and collide with greater energy, often leading to more successful reactions. Surface area is also important, especially in reactions involving solids. The larger the surface area exposed, the more particles are available to react, which can significantly boost the reaction rate. Then we have catalysts. These are substances that speed up reactions without being consumed themselves. They work by providing an alternative pathway with a lower activation energy. All of these factors, concentration, temperature, surface area, and catalysts, affect the number of effective collisions between particles. The more effective collisions there are, the faster the reaction proceeds, and that ties back into our overall theme of understanding how to control and optimize reaction rates. Let's talk about the effect of concentration on reaction rates. When we increase the concentration, we're essentially adding more particles into a given volume. This means there are more particles available to collide with each other. And as you might guess, more collisions generally lead to a higher reaction rate. For example, take hydrochloric acid reacting with zinc. When the concentration of hydrochloric acid is increased, the reaction happens faster. That's because the increased number of acid particles results in more frequent collisions with zinc atoms, speeding up the process. So the key takeaway here is that increasing concentration boosts the number of particles, which in turn increases collision frequency and speeds up the reaction. This concept ties into the overall theme of how different factors influence reaction rates. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's talk about the effect of temperature on reaction rates. When we increase the temperature, it causes the molecules involved to gain more kinetic energy. This means they move faster, and as a result, they collide more often and with greater energy. These more frequent and energetic collisions make it more likely for reactions to occur. A key rule to remember is that the reaction rate generally doubles for every 10 degrees C rise in temperature. This connection between temperature and reaction speed is really important because it shows how sensitive reactions can be to even small changes in heat. Overall, understanding this helps us see how controlling temperature can influence chemical processes significantly. This slide doesn't contain enough information. That's why we're moving to the next slide. Now, let's talk about the effect of surface area on reaction rates. Reactions tend to happen faster when the surface area is larger. For example, powdered calcium carbonate reacts more quickly than marble chips. The reason for this is pretty straightforward. When you have more surface area, there are more particles exposed. This means there are more spots where collisions can happen, which increases the likelihood of a reaction occurring. So, essentially, increasing the surface area provides more opportunities for particles to collide and react, speeding up the process. This concept ties into the overall idea that many factors influence reaction rates, and surface area is a key one to consider. A catalyst is a substance that changes the rate of a chemical reaction without being consumed in the process. Essentially, it helps the reaction happen faster or slower, depending on what's needed, but it doesn't get used up itself. There are two main types of catalysts: positive catalysts, which increase the reaction rate, and negative catalysts, also known as inhibitors, which decrease the reaction rate. For example, in the Haber process for ammonia production, iron acts as a catalyst. It speeds up the reaction, making the process more efficient. Understanding catalysts is key because they play such a crucial role in industrial chemistry and many natural processes alike. This slide doesn't contain enough information. That's why we're moving to the next slide. So, in conclusion, chemical kinetics really helps us understand how and why reactions happen at different speeds. It's all about grasping the key concepts like the rate of reaction, which tells us how quickly a reaction occurs, and the rate constant, which is a specific value that relates to the speed of a reaction under certain conditions. We also look at collision theory, which explains that molecules need to collide with enough energy and proper orientation for a reaction to happen. Factors affecting reaction rate include things like temperature, concentration, and surface area. Basically, what makes reactions faster or slower. Another important point is the role of catalysts, substances that speed up reactions without being consumed in the process. These principles aren't just academic. They play a vital role in industries, medicine, and environmental chemistry, helping us develop better processes, medications, and sustainable solutions. Overall, understanding these concepts allows us to control and optimize reactions in many practical applications, making chemical kinetics a truly valuable tool across various fields.